There you go. Yeah, so um I was watching on YouTube about oops, what's happening? About different the video just showed up graph neural networks on YouTube, and I just look at the different videos. And at some point they kind of give a surface knowledge, but they don't go too deep into the details. So I figure I want to go deeper a little bit into the detail of graph neural networks. So let's see what's actually in there. So I look it up and I found this paper, a Zento Introduction to Graph Neural Networks. That's for me, it's pretty helpful for me to actually, a little deeper into neural networks. Just build up on the basics I already knew from, let's say, YouTube video that I watch. So the first, their hook is there's a bunch of practical applications, and this is like their list of practical applications. For me, like from the previous presentation, I already know some of them, like antibacterial discovery. This is like drug discovery. So you have a molecules, and then that's a graph right there. And I knew traffic's prediction already. The traffic is just you have a bunch of intersections, a node, and the row is the edge, and then you have a graph right there. And the map is a graph itself. A recommendation system also very popular for graph neural networks. As what student watch next mainly to predict the link of the two nodes. Like different movies going to be different node, and your order of watching them or how they're related is going to be the edge. But they list a few things new that I didn't expect. So let's say physics simulations. I didn't expect physics simulations. They apply graph neural networks in physics simulation. So if you click on the link, they can lead you to this paper. But if I pretty interesting, that let's say this is water inside a tank, and this is like gravitational, and they're gonna assume that each molecule of water molecule is gonna be a node, and then they make a graph out of it, and then like this is how the graph change over time based on gravity. So that's pretty interesting thing to look at for graph neural networks. And another one is fake news detection. So they were able to somehow use the news and this influencer on social media, and after the check, the who follow who, that's the link. And then the node is going to be like the account is a node. You can use the link between them to know if the news is fake or not, stuff like that. Is someone manipulating this news, or is it actually solid news? So that's pretty interesting. Two new applications I can know of from the paper. And then this next thing the paper do is give a very basics of the graph neural networks with I already did it on the last presentation. So they introduced node, which is this kind of node. But for formal context, they also use vertex for node. So the vocabulary have the same meaning. You can use either vertex or node. For edge going to be the link between the node, so edge or link. To formally use as edge. And for edge, you have directed edge, which you generally go one direction from one node to another. Or you can have undirected edge, which you can go both way, one node to another, and the other way around. Both way works. And then for graph is the whole thing, so it's the basics. It's going to be the combination of node and edge together. And they call it global or master node. So that's the new vocabulary that they formally use in the paper. The global master node. You may encounter them when you read more paper. And it's also another review. So, graph neural networks make up of graph, node, and edge. So a graph neural network can predict this three component, right? It's the either is this is node level predictions. So you have all the data, you can predict what this node is. In this case, they give an example. Does this person smoke? So you can label this node with either smoking or not smoking person. And here's a edge level predictions or link prediction. Edge or link are the same thing. This is the example is next Netflix video. So the link is going to be like which is the next video they're going to watch. And here we have the graph level predictions. So we predict the whole thing as the graph. And this is the famous example of graph neural network. Is it molecule a suitable drug? So is this molecular structure is good for our purpose? This is actually the one that make graph neural network famous, I think. Like this is the one that stand out. And here's actually they go is into the paper. So they go over graph network. So there's not much of neuron into it yet. They explain how the graph itself, on some basic definition, the terms that we may encounter later in the paper. And so they mention touch on the challenge of using graph in machine learning, that the difficulties that we have to deal with. The first definition is the connectivity of a graph. So for just the basic definition of graph in our context, it has to be, it has to have the connectivity. So this is a graph with a connected graph. So graph with connectivity. So if you pick two random point on the graph, so let's say 4 and 6, right? You can go from 4 to 6 to the edge in the node. So that's the definition. So 4 to 5, 5 to 6. And let's say you pick 1 and 5, you know, 1 to 3, 3 to 4, and then 4 to 5. So it doesn't matter how you do it. You pick two random points, two random node on the graph. You should be able to connect them through the edge and the node. So that graph has the connectivity. On the other hand, if they don't have the connectivity, then they disconnect it. And you cannot, if you pick, let's say 1 and 4, you're gonna go 1 to 3, but you cannot go to 4. There's no link between 3 and 4. That's the definition for connectivity.
Wait. So
Yes.
would it be a disconnected graph? That's just basically just two separate graphs, isn't it?
Yes. Yeah. There's two separate
Okay.
connected graph. Yeah. And another thing they mentioned is the adjacency matrix. So in adjacency matrix, I think they mention it because computers like to compute matrix. That's the basics of like discrete basis for computing. And so they have a graph, but how do you represent it for computer, right? So one of the solution is use a adjacency matrix. So for this matrix, so let's say A and C is connected. So A and then C over here, and then A and C is connected. You have the blue um the blue box right here. And then B and C is not connected, so you can go B and then C is gonna be not blue, it's like white box. Then let's say B and D are connected, so B and D are connected. You have it right here. Then same thing over here. B and D are connected. It's gonna be blue over here. So they just convert a graph into a matrix. So that's the adjacency matrix. And this is another example of adjacency matrix. So this one you can go also with the directed edge. So this is the from. So from this node to this amount of node. So let's say we can go from 1 to 4. So from 1, so you go over here, 1 to 4, there's 1 over here. So yes, there is an edge between 1 to 4, and let's go from 1 to 4. And then let's say 1 to 3, there's no node, there's no edge going from 1 to 3. So we can see 1 over here and then 3 over here. It's gonna be 0. So there's no link, but there's no directed edge going from 1 to 3. That's an example. And then like let's say 0 to 2, 0 to 2 should be 1. So yes, there is a link between 0 and 2. So that you just convert the graph into a matrix. That's the adjacency matrix. And the problem with this matrix is the one of the challenge when you're going to do neural networks with this kind of stuff is that it's not very computationally efficient because it's an order of n square. So let's say you have n node, 1, 2, 3, 4, you have like 4, 5 node. Then you have the matrix, which is like 5 by 5. So that's not very efficient for computing n square stuff. And so what they come up with is an adjacency list instead of a matrix. And like for list, it's like a vector, and computers also can compute vector efficiently. That's good. And for adjacency list, you simply pick the number of node and then let's say 0. Then this 0 is going to connect it to 1 and 2. So 0 to 1 and 0 to 2. So that's how they compute the list. And same thing here. If you pick 1, so 1 over here, it's going to be connected to 0, 3, and 4. So 0, 3, and 4. Then you continue doing that. 2 is going to be 0 and 3. So 2 is going to be 0 and 3. That's how they make the list of the adjacency list. And then now they move on. So after explaining this like basic vocabulary for a graph into matrix and list, they actually go into the neural networks problem. So for that definition, for neural networks, so let's say you put an input into GNN, so graph neural networks, and you get an output. So let's treat it as a black box. Then between the input and the output, what change is going to be the edge going to change, like the information is going to change, the node information may going to change, or the global, remember global is going to be the graph itself. The global is going to change. But what's not changed is the connectivity shouldn't change. So if it's one graph, one fully connected graph, it shouldn't change into like two different connected graphs. It shouldn't be disconnected. And also the adjacency matrix and the adjacency list also not going to change. So that's the basic definition. Then here they start to introducing more detail of the graph neural networks. So this is one technique to prediction of graph neural networks is using pooling information. And pool information so why do you use that? So let's say you know the vertex of the graph. We have a graph here, and you know all the vertex, you know all the node, but you don't know the link between the edge between them. Or maybe the other way, you know the edge, you know the connection between them, but you don't know the vertex, you don't know the node, what's in the node. Or maybe another case is you know all the vertex on the edge, but you don't know the global. This is kind of odd. I don't exactly know what they mean by that. But anyway, the list of steps is first for each item to be pooled. So let's say you want to pool this item and this items. You gather information, gather each of their embeddings and concentrate them into a matrix. So let's say you take this node for you're interested in to pool this node right here, vertex. Then you're gonna take the neighboring edge, take the information from the edge, the two edge over here, and you put them, and then you add them up. So that the gather embeddings are then aggregated. So it's a function. It's usually via sum operation. It's just a function that you make, you add the two information, and then you sum them up, and then you put through a function, and you get an answer for this node. So you can predict the information in this node using the two edge. So that's the idea of pool information. And similar here, you predict a vertex using the edge. Here you can predict an edge using vertex. So this is the graph, this node, this edge. V stand for vertex and E stand for edge. And this row symbol stand for aggregate function, so pooling function. And then here, they aggregate the vertex to the edge. So they take the input is going to be the vertex. You take all the vertex in, and then they aggregate it, and then the answer to be output the edge information. And the C is just the classification. It's a basic neural networks. And through this neural networks, they can predict like what's the edge, classify the edge and what they are. Same here, they have an example of a vertex edge, and then they predict the global to the graph itself. So here they have the global, and this is the graph. They have global, they have vertex. Here the input is all the vertex, and then they get the global. Say similar over here. Just you have information, and then you aggregate it, and you get the other information.
Wait, I have a question about this because I actually read
Yes.
this
Hmm.
this essay that you're discussing.
Hmm.
So polling, is it just like adding all the vectors describing the edges together, or is it more sophisticated than
Um, well, it doesn't have to be adding. It can be a function too.
that? Okay,
Yeah.
so just anything that has to do with the vectors of the edges. It depends on the network.
Yeah. Hmm. And
Okay.
the special thing about pooling, I think, is it focus on let's say you have one node and you focus on the edge between in connect to that node. So when I first learned it, I learned message passing, which is you go from one node to the other node, but he has focused on the edge of that node. So instead of the other node, that's pretty
Yeah, okay.
interesting. Yeah. Oh yeah, and here you go, the passage meshing, this mentioned. So they say we do passage meshing, passing message between parts of the graph because we need to be aware of the graph connectivity. So, well, I mentioned the connectivity, so make sure that it's one piece of graph and then you pick 2 point and you can go from one node to the other node through the graph. It should be the same way. The information goes both way. So that's what I figure out instead of one way like pooling. So for pooling, let's say you go from the edge to the node. You don't go the other way around. You don't go like one node and you divide it into two edge. But in here for passive meshing, you actually it's like you go from one node to the other node, but also at the same time the information from the node go back to that node. So they exchange message. So this one is the step. So the first step is for each node in the graph. So it's not just the node we're interested in, but it's for like every single node in the graph. But this one is for each item to be pulled. So it's different in the definition in that way. And we gather as the same step, whether they are the neighboring node or edge. So it doesn't have to be node. In most YouTube video I watch, it's like node only. They don't really mention edge. But here they can show that it can be both ways. And then same, you aggregate all meshes via an aggregate function. And then here, the last step is just for neural network. It's learning the pull meshes are then passed through an update function. This is for neural networks part to learn through different step and learn through loss function. So this is the example I take from YouTube of message passing. So this is exactly what happened. You look at one person, it's gonna take the information from this person, this person, this person, and itself too, and then it changes um, change the node. So this one is a node and this is the link. So the node itself gonna change information. This is a passing message between parts of the graph, and then this one is I think I focus on one node. Oh yeah, it's pretty much the same as this, but it's represented in the paper. So they represent it in a way that if you look at what this node, focus on this node, we're gonna take information from its neighboring node. So this node and this node gonna be put in here, and this node gonna take information from itself too. Then you add all the three information together, you got this vectors, and you put it into a transform function, and then you get this updated node at the next layer. And then similar to other node as well. So they do this for every single node. And they compared it with convolutional neural networks, so CNN, and graph neural networks. So they do compare them. And you can see the similarity is that both aggregate and process information uh, of the neighboring element. So for convolutional, you also you look at one and then you take the like the canals like the neighboring pixels, right? And here same with the graph neural networks. You pick one node and then you take the information of the neighboring node. But there's a difference, which is just the basic difference of a node and the pixels. That's one. But also the more important one is in a graph, the nodes can be varied. For let's say an image, the neighboring pixel, the number of neighboring pixels is fixed throughout the image. It doesn't change that much. It's pretty much fixed. But for a graph, it can be changed a lot. So like this one have two neighboring, but this one can have like three neighboring nodes. So that's another difference. Then here we have, so this one is another way to represent it out in the paper. So you have, so this is the graph, you have the node here, you have the edge here. You have this the global, the graph itself doesn't change much. The edge itself doesn't change much, but we're focusing on the node. So still similar to the example, still the same thing, we just represent it in a different way. So this is the vertex. And then we have the aggregation function. It's going to go from vertex to vertex this time. So you're passing message from this node to this node and this node to this node, just between the node only. And you get a next layer of the graph. So it's going to be different. Then the other thing is the same. Rho is the aggregate function, and F, which is an update function, is neural networks applied to learnable variable. Then here, so this one is just go back to vertex, go back to vertex, but you can also have other variable in that. So you don't have to like vertex, go back to vertex. You can go from vertex to edge. So remember this is like pooling. You can go from one component to the other component. Let's go from node to vertex first, and then from vertex you go back to node. So that's also one way for you to do it. And then there's like a bunch of other ways if you want to. You can go to node first, pooling to node first, then you pull into edge. You can pull into edge first and then pull into node. Or you can do this weave layer too. You can pull to node and pull to edge at the same time. And then the second time you're gonna pull to node and pull to edge at the same time. So there's a lot of variation in the way that you can do pooling and passive meshing.
Wait, can I just make an observation?
Yes.
So a lot of the times that the models that I'm learning about,
Hmm.
they don't really do anything with the edges. The edges are just
Hmm.
used to connect the nodes, but they don't really have any values in and of themselves.
Hmm. Yeah.
So it
Right.
basically just involves passing between nodes.
Hmm. Right.
There probably are some exceptions, but that's kind of the most common ones I've come across.
Hmm. Yeah, that's what I noticed in the YouTube video too. So I was very surprised to like see this and learn new stuff like this.
Yeah.
Yeah. So
They
it
don't,
is it
it'd
is
be interesting
possible.
if they're,
Hmm.
okay, go ahead.
But yeah, no, you good. We'll just say, yeah.
I was just wondering if like graph attention neural networks, you could treat the attention weights as the edge values, but I never heard that mentioned explicitly.
Let's see. Yeah.
But yeah, I don't know.
See. Yeah. Okay. I was saying it's pretty interesting. Yeah. To see the difference between this paper and other paper. But yeah. Anyways. Yeah, so the next they go for adding global representations. So the reason they do this is because if the graph, there's a node that's too far from the graph, so it's still connected, but it's like one long edge that's like really far away, then it won't pass this information into the other node because you need to do too many aggregation steps to get it into the main graph. And the solution is you can pass all node information to each other. So this is attention mechanism pretty much, I think. But that's a little bit too much computationally for them to do. It's also called virtual edge, like I mentioned. So the solution is they're gonna use a global representation U. It's called a master node, and then they can refer to the context vectors for the very far node. So they can like take all the node in the graph into account. So this is yeah, this is how they do it. So they have, let's see, oh yeah, that's it. That is the end. So um they have a node embedding adjacent node. Oh yeah, so they have so the embedding of the node itself. So let's say we embed the node, and then we take into account the adjacent node. So this node can have this node and this node, and then you take into account the edge of the node. So this edge and this edge. And they also take into account the global embedding. So the whole graph. There's like one other vertex that take into account the whole context of the graph. Then you take all that into account, then they get to the updated mode embedding. So a new node is gonna be taking into account of every single thing that's neighboring to that, plus the global understanding of the context for the updated. Yeah, and then I stopped at here. There's more to this paper. I'll probably present the next part next time. Yeah.
Awesome, this is pretty good.
Hmm. Yeah. Thank you.
Yeah, it's kind of overlaps with a lot of the stuff that I've been learning about.
Yeah. You have any like other question on this
I'm trying to
presentation?
think. Oh yeah, the adjacency list. Oh, I'll just make a comment on that because I think you touched on this earlier, but it isn't all. It's so you mentioned how like the adjacency matrix was very expensive. It takes a
Mm-hmm.
long time to compute because it's so
Mm-hmm.
big. Another
Mm-hmm.
reason is that you can actually permutate it a bunch of different ways. You can reorder
Oh, right.
the nodes, and
Mm-hmm.
it means the same thing, but a
Mm-hmm.
neural network is going to read it differently.
Right. Yeah, yeah.
And so that's
Right.
another reason why they use an adjacency list
Right. I
because there's
see.
only one way to represent it.
Mm-hmm. I see. Yeah. Yeah. I remember they do something like that too. Like they sell a bunch of different matrices. So I see.
Yeah.
Yeah, that's
And the
very
bigger they
important.
get, the more you can make.
Mm, yeah, true. Yeah. Mm-hmm. Right.
That's really all I have to say.
Right. Yeah.